All right, so let me show you how you would put this one together then. And this is kind of a nice problem. I like this problem. I like all these problems. What am I talking about? All right, because, you know, now you're kind of putting the calculus to use here a little bit. Okay, so let me reload this thing real quick. Okay, so what we need to do is we need to, of course, find equations on this. So we got to do a little bit more work with our diagram here. Okay, so x is the size of the square we're cutting off. Now, if you look at this problem, the way it started was kind of like this. Okay, it said that, I think it said the dimensions were 12 by 16. So it means originally, this whole slice right there was, we'll say that one was 16 inches. And then originally, this dimension, the whole entire thing, was 12 inches like that. Okay, so what would this little slice right here be? Because see, if you cut off the x's, this would be the new size of the box. What would it be?
16 minus 2x.
Good, 16 minus 2x, right? It's the whole thing 16 minus 2 of the x's. So that thing right there is 16 minus 2x. Okay, so that's a key dimension that we're going to use. Okay, and then by the same thought process, what is this little piece right here going to be?
12 minus 2x.
Yeah, 12 minus 2x. Okay, so you got to get everything represented algebraically then. So you've got now your length, 16 minus 2x, and you got your width, 12 minus 2x. What's the height? What are you folding up? How tall is that thing going to be? X, okay? See how tall it is going to be this dimension right here. You can think of that flap right there as being x tall, okay? So if you looked at this diagram right here, this would be kind of what we're doing. This is like 16 minus 2x there, 12 minus 2x here, and then x there. Okay, does that make sense to everybody? Because that's the whole key to the problem right there. That's the key, all right? Now, always pay attention to what you're maximizing or minimizing. You're maximizing volume. So what we have to do is we have to have a function for volume with one variable. So how do you find a volume of a box? What's the formula?
Times width times height.
Yeah, exactly. So we got the volume is just equal to length times width times height. So, and we're only going to have one variable. So the length is going to be given by this thing. So that's 16 minus 2x. Okay, the width is going to be given by this thing. Okay, so that's going to be 12 minus 2x. And then the height is going to be given by x, like that. So that's going to be the function that we're going to differentiate then. Okay. Now, what you want to do on that is, you know, if you want to differentiate that, probably the smartest way to do this is just multiply it all out. So you can use power rule and stuff. So let's go ahead and let's FOIL this part right here. So let's see, we got, you can just kind of do the FOIL, use your calculator a little bit if you need to. So 16 times 12 is 192. Okay, and then the outside term is going to be minus 32x. Inside term is going to be negative 24x. And the last term is going to be positive 4x to the second. So I'm going to clean that up a little bit and write that as 192 minus 56x plus 4x to the second times x. Then you want to go ahead and distribute the x through there. So you can go ahead and do that. So we're just taking x times 192 is 192x. X times 56x. 56x the second. And then plus 4x to the third. Okay, we have a third power in there because volume is in cubic units. That's the way it worked out. Okay, so we're all set up and we haven't even done any calculus yet. The calculus just takes a couple of quick steps. So I got to find critical points. So if I find critical points, what do I do? Find the derivative, see where it's undefined or see where it's zero. So we're going to go ahead and do the derivative. This is a polynomial function. So if we do the derivative, we're going to get 192. Power rule is what we're doing, minus 112x, and then plus 12x to the second, like that. Now, sometimes these problems are designed so that they factor, sometimes, unfortunately, you got to use a quadratic formula. So we're going to go ahead and set that equal to 0 and solve the equation. Now, one of the things that you always want to kind of look at on this is see if there's any common factors. Well, they all divide by 2. There may be something bigger, though. I'm going to just experiment a little bit here. I suspect they all divide by 4. Maybe even 6. No, 4. All right, so let's divide everything by 4. Now, see what you can do is you can divide by a constant, but what I've said before is don't ever divide by a variable because you would lose possibly a critical point if you did that. So we're going to have 0 is equal to, and we have 192 over 4. So that's 48. And then we've got 112 divided by 4, which is 28. And then plus 3x to the second like that. Okay? Now we'll have to see if this factors, because I think I've got everything on here okay. Got all my arithmetic okay. Okay, it may not factor. And if it doesn't factor, you just go immediately to the quadratic formula. I'm kind of tempted on this one. Well, let's try it and let's see. I haven't worked this one out, so let's see if we can get anything. I'm going to rewrite this as 3x squared minus 28x plus 48 like that and just see if it factors. So let's try a 3x and x. 8 and 6 maybe. Maybe the other way. If not, then don't waste your time. Just go to the quadratic formula. So let's say, I know that ain't going to work. 6 and 8. What else we got? 12 and 4. Yeah, I don't know. I'm a little skeptical. How about you? It may factor, but I'm just, a lot of times what I do on this is just, I'm wasting my time. If it factors and I can't figure it out, I'm just going to go to the quadratic formula. All right, so let's just go ahead and plug it in and see what we get. Okay, and you're going to have to deal with this some. So let's see, x is going to be equal to negative b, so that's negative 28, plus or minus square root of b squared, so that's negative 28 squared, times 4ac. Okay, now c is 48, so then a is going to be 3. So we got 4ac, and then all over 2a, and then the rest of this I'm just going to get my calculator out, and I may end up, probably on this one, I'm just going to get a decimal and that's good enough. So I'm going to do 28 squared, which is 625. No, that's not right. 28 squared is 784. So I got 784 minus, and then I have 12 times 48. It's going to be 576 all over 6. And see, what I'm going to go ahead and do from here is I'm just going to mostly just get the calculator out, not worry about simplifying it. So 784 minus 576 is going to give 208, I think. Then let's just go to the calculator. Now I'm going to pull the calculator up here because I'm going to just get decimal answers anyway on this one. So, and then I'll show you how you can check this on the calculator. So what I'm going to do is just go 28 plus square root of 208. I like that. Just get the answer and then divide that by 6. Okay, and so you're going to get an irrational number. That means it wouldn't have factored anyway. So we're going to write one of the answers is, let's just round that to 7.1. So x equals about 7.1. Now the other answer probably doesn't make any sense. So if you did 28 minus the square root of 208, okay, you're going to get a negative, no, I guess you are okay on that one, and then divide by 6 like that. Okay, yeah, so we get a second answer of x equals about 2.3. Okay, so that's quadratic formula. So is there any question about the algebra or the derivative or any of that stuff? You got to deal with quadratic formula. Now, one of those answers makes no sense. Which one? Go back to the original problem. The original problem, what were the dimensions? The dimensions were 16 by 12. Okay, so what would happen if you tried to take a pair of scissors, and this thing's 12, and then you cut it 7.1 by 7.1? It wouldn't work, would it? You don't have enough room, so that's no good. That is probably, it's a critical point. It may very well be a minimum or a maximum. So it looks like the appropriate dimension is about x equals 2.3, like that, okay? Now, before we write the answer and everything, one of the benefits of graphing on these things is you can do a lot of the arithmetic too. So if you go back to the volume function, and I always recommend if you're going to check this on your calculator, why don't you just check it here? Okay, because what if you messed up on your multiplication and stuff? It's just as well when you check this graphically to put this in like this. Just put in the 16 minus 2x, and then multiply by the 12 minus 2x, and then multiply by x. That's the way I'm going to check it, okay? Just do that, okay? Now let's see, for a window, well, x, the minimum of x is 0. Why? Because you're cutting out a corner, okay? You can't cut out a negative corner of something. Let's see. Now, the smallest side is 12. So what would be the biggest dimension you could use if you cut out two squares if something's 12? 6, okay? So you could do 6, and the problem doesn't make any sense once you get past 6, okay? It's kind of like the 7.1, it was too big. Okay, then for our volume, that's 0. Now what you'd have to do is just kind of take an educated guess or something. You can even look at your table of values. I'm going to start by doing this, and you're going to see a cubic function, and you should see a maximum at 2.3. Okay, and I probably made the y's too big, but that you get the point. It doesn't matter. So now what I'm going to do is I'm going to trace at 2.3, and then the volume's going to pop out. Okay, right there. So if you look at this, the volume is 194 cubic feet right there. See, that's the size of the square you cut off. That's the volume. Okay, so then you can use your calculator to kind of assist you with that a little bit then. Okay, so we've got the problem solved, and on the calculator you can pretty well tell that that's a maximum. So the dimension that maximizes the box is going to be 2.3 feet is what you're going to use, and that volume is 194 approximately. We rounded, so the maximum volume is approximately that. Okay. Okay, so that's how you would go about doing all the parts of that problem. Does that make sense? Okay, so it's all about building a function that you can differentiate. So the ones that I've done so far are pretty standard, not too hard, because they've got polynomials in them. Any questions before I do this last one? Because the last one's harder. Okay, is that good? Okay, so optimization, the biggest thing that you got to do is work with getting the equation and one variable that you're going to differentiate. Okay, so here's kind of an interesting problem. You can do all kinds of these problems that are geometric in nature. So what this problem is saying is that you have been asked to design a 1 liter oil can shape, like a right circular cylinder, so I drew out a cylinder. What dimensions will use the least amount of material? So this one is a minimization problem, like that. So what we got to do is we got to figure out what we're minimizing. So when it says material, okay, that's implying what's outside of the cylinder. So what do we call that? Surface area, good. So what we're going to do is we're going to minimize the surface area. Okay, there is a formula for the surface area of a cylinder. I don't know it, but I know how to figure it out, and that's what I'm going to show you how to do. So we're going to minimize that surface area. Okay, so if you look at the surface area, and I tried to draw this out, and this will probably help you understand this. What I tried to do was unfold the cylinder. So think about this. You have two circles, right, the top and bottom. Does it make sense that this is a big rectangle? Yeah. Okay, it's got to be, because you're just wrapping it around a circle like that. So what we have is the height. The dimensions of this is you're going to basically have, this is the height. I already put that on your paper. That's the height right there. Okay. The circle is only dependent on its radius. Okay. Now let me ask you what this 2 pi r means. I put that on there. You know what that is? That's the circumference of a circle, right? So if you think about this, does it make sense that the length of that rectangle would have to be the distance around a circle? Okay, that's the circumference. Okay, does that make sense? Okay, so we got everything we need. If we're going to do the surface area, I'm going to abbreviate that, surface area. Well, we have two, it's going to be this. It's going to just be the area of the circles, which we have a formula for that hopefully we know, plus the area of the rectangle. Okay, there's a formula you can look up for surface area of a cylinder, but it's better if you just figure it out, okay? All right, so what's the formula for an area of a circle? Yeah, the area of a circle is pi r squared, and we have two of those, so I'm going to say 2 pi r squared. Okay, that's the area of the two circles that we have. Okay, the area of a rectangle is, what do? You do base times height, their length times width. So the base is 2 pi r, the height is h, or length times width, so that's just going to be 2 pi r h. So this is going to be what we minimize. I'm going to call this S of, and right now we have two variables. If we were in, Calc 3, where we use two variables that we can differentiate with what we call partial differentiation, and we could work the problem out maybe this way. But what we got to do is we got to find another equation because we have too many variables. We got to get it down to one variable. All right, so does the surface area equation make sense to everybody? Okay. Okay. All right, so now they gave us another piece of information. Okay, they gave you that you got a 1 liter oil can. Now, what's 1 liter? That's volume, right? Okay, so we can find the volume of this cylinder, and that's going to be equal to 1, and that'll give us an equation that'll probably help us with this. Okay, so the volume of this cylinder is like this. Now, you may not know the formula, but it's easy to think about. You can think of a cylinder as a bunch of circles stacked on top of each other. So, what is it? What is the area of the circle on the bottom?
Pi r squared.
Okay, so it's pi r squared times h. Okay, then h would be those circles on top of each other. So that's the formula for a volume of a cylinder. Now, you can look that up if you need to, but you can reason that out too. Does that kind of make sense? You got a circle, and there's h high. Okay, kind of like that, and that's volume, okay? All right, so what we're going to do is that volume is equal to 1, so we're going to say 1 equals pi r squared h. Now we can solve for either variable. We can either solve for h and plug it in, or we can solve for r and plug it in. I think it's easier to solve for h, because if we solve for r, we'd have square roots, because we'd have r squared equals something, and we'd have to introduce square roots. So we're going to go ahead, and we're going to solve this for h. So what we end up getting then is h is equal to 1 over pi r squared. And that thing right there gets plugged in right there. Okay, now we're going to be down to a function with one variable, so then the calculus takes over now. Okay, does that make sense so far? Okay, so I gave you a volume of 1, so what we're going to say now is we're going to have 2 pi r squared plus 2 pi r. Now let's replace h with what it's equal to, 1 over pi r squared. Okay, and we're going to simplify this. So see, the variable we have now is r. So we can differentiate this with respect to r, and we can find h if we need to. Okay, so before we do our derivative and find our critical points, we're going to simplify a few things. So this is 2 pi r squared here. If you look at this piece over here, this is 2 pi r over pi r squared. Well, what happens? Well, the pi's cross out. And what else? One of the r's crosses out because you have that, so it's 2 over r. So I'm going to go ahead and write that as, when you multiply all that out and everything, you're going to have 2 over r, but I'm going to go ahead and write that as 2r to the negative 1 because I got to do a derivative anyway, and the power rule's the best way to do that then. Okay? All right, does that look okay? Okay, so you can kind of see a typical, all of these problems had something in common, and it's basically there was something that a function you differentiated, and most of the time you had to come up with an equation so you could get your equation with one variable that you differentiate. That's the key, all right? So now let's do the derivative. This is a pretty standard derivative here. All right, so what's the derivative of 2 pi r squared? 4 pi r, right? Because you're doing power rule. You can just multiply the 2 by 2. Then the next one is going to be minus. You're going to bring down the negative 1. So it's minus 2r. Subtract 1 from the exponent so you get that. So you're going to have s prime of r is going to be equal to 4 pi r minus 2 over r to the second like that. Now what we got to do is we got to find any critical points we have. Okay? Critical points occur where it's undefined. Is that thing ever undefined? Yeah, okay. If r is 0, then you're going to have a critical point. Okay? But a radius of 0 isn't going to make any sense in this problem because you won't even have a freaking cylinder, right? All right? So that doesn't make any difference. So what we're going to do is just go ahead and set it equal to 0. So we got 4 pi r minus 2 over r squared. Then we need to solve that equation, and then that probably is going to pop out and give us the answer. So we have 2 over r squared equals 4 pi r. And there's a couple of ways you could do this. This is a proportion. You could cross multiply if you want to, and if you did that, you would have 4 pi r to the third is equal to 2, like that. Then you'd have to divide by 4 pi. Okay, and if you simplify that, see, that's going to cross that out and leave you r to the third equals 1 over 2 pi. Okay, then what? Cube root, right? Okay, you guys are looking at me funny.
Oh, because you swapped around once, right?
Yeah, that's what I did. What I did was I moved this thing. And the reason I do that is because it had a negative. I mean, it doesn't matter. You can get the variables on either side. It doesn't make any difference. So I moved that over there. Then I cross multiply. So I have 4 pi r cubed equals 2. Divide by 4 pi and then reduce the fraction. So does that look okay now?
And how did it get to 4 pi r cubed from 4 pi r?
I cross multiplied. Okay, so you got a proportion. Okay, so you can do it that way. The other way is you can multiply both sides by r squared to get rid of the fraction r squared. Okay, now you're going to do a cube root of both sides. Okay, so we're going to end up with this critical point. R equals, and see, this is really the cube root of 1 over the cube root of 2 pi. So the cube root of 1 is 1. Then we have the cube root of 2 pi. So that is a critical point like that. Okay. Now we got to find the dimensions of the cylinder. Another thing I wanted to show you guys, I haven't talked much about this, but we're trying to find a minimum. And without going to your calculator, you can do what we call the second derivative test, which has a lot to do with concavity. So I do want to show you this because this is something you ought to look at in these problems. I've been kind of basically just doing the graphing, but you can also do it this way if you want to. You could go your first derivative, s prime of r, that was equal to 4 pi r minus 2r to the negative 2. And then if you do the second derivative, you're going to get 4 pi, when you do that derivative, plus 2r to the negative 3, like that.
4.
Okay? No.
4.
Oh, 4. Yeah, that 4. Okay, I thought you were talking about the exponent. Okay, sorry. Okay, so 2 times 2 is 4, so we have that. All right. Now what would happen is you would have 4 pi plus 4 over r to the third. Now, what I'm going to do on this is the second derivative test. You take the second derivative and you replace r with the critical point. And you don't have to work this out. You don't have to work it out at all. I'll explain that. So you just got to figure out if it's positive or negative. So if I do this and plug this in, it's 1 over cube root 2 pi to the third. Now I want you to look very carefully at that expression. You don't have to work it out. Do you think it's positive or negative? It's positive because 4 pi is positive, right? And then this is a positive number. 4 is positive. The denominator is going to be positive when you cube it, so it's positive. So here's the idea. Remember concavity? I gave you these little things here, okay? If that turned out to be positive, then it means you're concave up at that point. If that turned out to be negative, then you're concave down. But the thing is, this is a minimum, okay? Because I always kind of teach it this way. It's like the bottom of a chin. That's a minimum, right? So if the second derivative evaluates it positive, that means you have a minimum. Does that make any sense? You guys remember the concavity we went over last week, okay? So the second derivative test comes in handy. If you want to make sure that you have a minimum, that pretty well makes sure that it's a minimum right there without having to graph it. So you can second derivative, plug your critical point in, and then evaluate it. If it's positive, it's minimum. If it's negative, it's a max. And that visual will help you remember that. That's called the second derivative test. Okay, so we got one other thing we got to do. So the dimensions are going to be r equals 1 over cube root of 2 pi. We're not going to get decimals, just leave it alone. Now it just leaves us with finding h. So when we find h, one of the easiest places to work with h is right there. Okay, so we're going to plug in the r we found there, and then we'll have the other dimension. So h is going to be equal to, I'll just kind of put this in here, 1 over pi r squared, okay, like this. So we're going to plug in the r value that we got here. So that's 1 over pi times this whole thing right here squared. So it's going to be 1 over the cube root of 2 pi squared like that, okay? Now what I'm going to do on this is when I work this out, I'm going to go 1 over pi like this. Now when I work this out, if you square the 1, you're going to get a 1, so you don't have to worry about this. Then when you're working out like the cube root of 2 pi squared, the best way to write this out is just realize it's the cube root of 2 pi times the cube root of 2 pi. Okay, so that's going to be the cube root of 4 pi squared. So we just have cube root of 4 pi squared there. Okay, and then the only other thing you really probably want to do on this is probably what you're doing is you're dividing by a fraction. You're really dividing by 1 over that cube root. So when you divide by something, what are you really doing? You're multiplying by the reciprocal, right? So you could write this as 1 over pi times cube root of 4 pi squared, and then that would give you your other dimension. Okay, so I'm going to write this as, and this is getting sloppy, I know that. H is equal to cube root 4 pi squared all over pi. So believe it or not, that is your answer. Okay, those are your dimensions right there. Okay, and it can be checked too. We can look at this on the calculator here in a minute, and I'll show you how you can verify that then. That's pretty crazy, isn't it? Well, no, it's not really crazy. It's just got some complicated arithmetic in it. I sense that you guys were following along pretty good with the surface area and the volume and the derivative and everything. The rest of that's just a bunch of messy arithmetic. And that's what you get into if you're going to get an exact answer to this problem then. Okay, so those would be the dimensions that maximize or minimize the surface area then. Okay, and of course you could take your calculator and estimate those as decimals if you wanted to then. Is there any question about that? Okay, probably not the best test question there just because of the messiness of the arithmetic.